Hello and welcome to the first content lecture for Psychology's Credibility Revolution. I'm Julia Strand. One of the cornerstones of the scientific process is that work can be independently verified and replicated. If I do a study in my lab and report some particular finding, another lab should be able to replicate that same effect. If studies don't replicate, if there's inconsistency in the results, that's cause for some concern. There has been murmuring of worry in the science that research may not be as replicable as is generally assumed. In 2016, the journal Nature, which is one of the biggest named journals in all of science, conducted a survey that revealed that 70% of the scientists who responded have tried and failed to reproduce someone else's experiments, and more than half of those have failed to replicate their own experiments. So why might a study fail to replicate? What can go wrong? Let's use a hypothetical example. Let's say that the original finding was about whether or not eating carrots improves your vision. One study comes along and says people who were randomly assigned to eat a carrot eating intervention had better vision than those who don't. The second study tries to answer the same question and finds that, in fact, carrot eaters and non-carrot eaters had the same eyesight. So this can happen for several reasons. Perhaps the first study, the original study, was a false positive. That is, they identified some finding when in fact that finding does not hold out in the real world. It's also possible that the two studies conflict because the replication attempt was a miss or a false negative, that is, failing to identify a true effect. So maybe carrots really do help your vision, but for some reason that second study failed to find that effect. So two studies may also conflict because there was some unintended difference between the two experiments that accounts for the deviation. So perhaps the experiments were conducted in slightly different ways, either intentionally or unintentionally, and that change substantially affected the outcome of the study. So maybe study one made sure that people ate their daily allowance of carrots. They checked in and made sure they ate their carrots every day. But maybe study two didn't make sure of that. And as a result, the carrot eating group actually didn't eat very many carrots. So in that case, study two attempted a direct or exact replication, but they missed a key step. You got to make sure they're actually eating their carrots. Or it may be that study two may have been a looser or more conceptual replication. So maybe study one was done by giving 1-year-old babies carrots, or not, and then testing their vision 10 years later. And study two was done by giving college students extra carrots for 2 weeks and then testing their vision. So it may be simultaneously true that carrots improve your vision and carrots don't improve your vision, depending on when you get the carrots and how we measure vision. So in that case, these two studies aren't actually contradictory at all. This isn't a failure to replicate. They just demonstrate that another variable, like say age, affects the outcome. It's important to remember, write this down, put a star next to it. A failure to replicate doesn't necessarily mean that the original study was wrong. Over the course of the term, we'll talk a lot about how we can reconcile inconsistent findings and make sense of these conflicting results. So sparked in part by some notable failures to replicate, in 2015, a group of 270 researchers started a project called the Reproducibility Project, where they got together to try and replicate 100 recently published studies from 3 of the major flagship journals in psychology. Whenever possible, the researchers worked with the original authors of the studies that they were trying to replicate to ensure that they were conducting replications that were true to the originals. Having 270 researchers involved is an incredibly ambitious project. Nothing like this has been done before in psych. And after years of design and data collection and analysis, the results were reported in the journal Science. And here's what they found. Okay, so to orient you here, the bar on the left are the p-values of the original studies. The bar on the right are the p-values of the replication attempts. Recall that p-values lower than 0.05 are typically those that we call statistically significant. As you can see, the vast majority of the original studies were statistically significant, and the replications were much less likely to render p-values below 0.05. So the team found that 67% of the replication attempts did not show the original effect. That is, 2/3 of the studies failed to replicate by the criteria of statistical significance. We can also look at measures of effect size. So recall that an effect size is a measure of the size of the effect. If you have 2 groups, it's a measure of how much those groups differed. So in our eating carrots help vision example, if we had a big effect size, it means that the vision of the carrot eaters was much better than the vision of the non-carrot eaters. So the effect sizes of the replication studies were much smaller than the original studies, meaning of those that replicated, the effects were not as robust as they were in the original studies in general. These low rates of replication have replicated in other kinds of comparable projects. Now, as you can imagine, this paper caused quite a splash and was really a turning point in what is now being referred to as the Replication Crisis. Subsequent replication attempts have yielded similar conclusions. Studies are replicating at lower rates than generally assumed, and with smaller effect sizes than we would expect if all were rosy in our garden of science. Consensus is mounting that there is indeed some kind of crisis happening in science right now. These are the results of more than 1,500 researchers who were surveyed about their perceptions about whether there is a replication crisis, and you can see those shown in red and pink are the ones who responded, yeah, I think something's wrong. So this concern has really far-reaching consequences. Many in the field have become very concerned. If studies have failed to replicate, which ones are next? How do we know what to trust? How much policy is based on these studies that may in fact not be true? It then started to become clear that this is not psychology's problem, although we may be a particularly egregious offender for reasons we can talk about later. This is science's problem. And the factors that led to the crisis in psychology are present in many other disciplines. My favorite doom and gloom headline is this one: everything is crumbling. All right, so it appears that science is broken and we can trust nothing. Class is over, good luck with comps. No, don't worry, we don't stop there. Okay, the results clearly indicate that something about how we're doing science is amiss. But, as I mentioned earlier, given how many researchers have failed to replicate a study, how is it big news that things fail to replicate? One structural issue that may have obscured these low rates of replicability is that studies that do not render statistically significant results, including failed replications, are very difficult to publish. We refer to this as publication bias or the file drawer problem. Statistically significant findings go in journals, they get published, and non-significant ones go in the file drawer so nobody ever knows about them. So this means that the vast majority of studies that you read will report statistically significant effects. This is something you can be looking for as you're doing your comps papers. As you're reading, notice how many of these studies find support for their hypotheses. How many of them find statistically significant results? Well, if we survey the literature broadly, a review of the rates of positivity in the literature, that is the proportion of findings that show support for the hypotheses, reveals that the vast majority of published studies found support for the hypotheses presented. In psychology, over 90%. So when new studies fail to agree with published studies, it's most commonly the case that the published study found a significant effect in support of the hypothesis, because it's published, and the replication attempt did not. So let's think through this. Okay, if we set up our p-value cutoff to be 0.05, and anything that is lower than 0.05 is statistically significant, and anything higher than that is not. It means that 90% of the published papers in psychology have p-values that are less than 0.05. So does that mean that 90% of the studies worked? The hypotheses were supported as expected? No, it likely means that lots and lots of studies were run. What happened to the rest of them? Well, they may have never gotten published. They got run, the data were analyzed, the results were not statistically significant, and they ended up in somebody's file drawer. There's another possibility about what happened to those studies, and we'll talk about those in class next time. Okay, so as an example, if I were to flip a coin 100 times, and sometimes it's heads, sometimes it's tails, 50% each, if I were to only tell you about half of those tosses, I could make it look like I had a coin that was weighted, like I had a coin that almost always came up heads. But that wouldn't mean that I had a two-headed coin. That means I have a normal coin, and I have misrepresented the results by only telling you about some of them. So if we look at failures to replicate in the literature, one major issue seems to be that there are a lot of false positives in the literature. That is, findings that have been reported that do not, in fact, represent the true state of the world. Why don't we worry about false negatives as much? Well, given publication bias, given the file drawer effect, studies that fail to find statistically significant results, those negatives, are much less likely to get published. But we'll talk about some issues relating to that a bit later on in the term as well. So in this class, we're going to talk about a lot of problems that science has. Huge structural problems that may make us doubt the foundation of a lot of the things we've learned. But Importantly, we're not going to stop there. We're also going to talk about how we can fix the things that are wrong. There may be times in this class where we feel disillusioned about the state of science. I feel that way sometimes too. But I also love science in my bones, and I think it's the only system we have for understanding truths about the world. My hope is that this will ultimately be an optimistic class, because we are currently in the process of figuring out how to do science better. And the changes that we're going to discuss have the potential to drastically improve science and make our discipline and other disciplines more transparent, more reproducible, and more robust. To lead into our first class meeting, I want to tell you about one notable and highly publicized failure to replicate. You can think of this as kind of a case study that will build on and extend what you read about. You should take notes and pay attention to the details here because this is going to be relevant in our class discussion. We'll talk about two studies that disagreed with one another and why it might be that the second study failed to replicate the first and why the authors of the first study responded as they did. So our story begins in New York in the early 90s. A researcher called John Bargh was interested in the effects of priming on behavior. So priming is the idea that we can activate concepts in memory by activating related concepts. And priming has been well studied and well established in lots of realms. For example, we'll do a little demonstration. I'm going to say a word and I want you to shout or whisper, depending on where you are, the first word that comes into your mind after I say my word. Ready? I say something, you say something. Here we go. I say dog, you said cat, right? Most of you probably did. Okay, so this is priming. I made you think about dogs. It primed a similar related concept of cats, so that's the word that you said. So Bargh was interested in whether activating concepts can also affect people's behavior, what they do, how they act, etc. And the type of priming he was studying was how activating concepts related to aging, to being elderly, whether that can affect people's behavior. So NYU students were brought into the lab and given lists of words and asked to make a sentence out of 4 of the 5 words on any given trial. So in this one, a sentence you might make would be, he is always worried. Participants were randomly assigned to be in either the unprimed control group, in which words across lists didn't have any cohesive theme, or an age-related priming list, in which many of the words were related to aging and the elderly. Here's the list of stimuli related to aging. So participants read and unscrambled sentences that were either unprimed or primed to do with aging to activate the concept of being elderly. That's the independent variable. The dependent variable, the outcome variable, is the speed at which participants walked down the hall after the study was over. So an experimenter, just pretending to be hanging out in the hallway, started a stopwatch when the participants left the room, and then stopped it when they got into the elevator to leave. The expectation was that thinking about words related to aging would activate concepts related to aging in your mind, and that would then prime related behaviors. So many people are familiar with the stereotype that old people walk slowly. So the hypothesis was that thinking about aging should slow walking speed. Here's what they found. They found that participants who received the primes related to aging walked down the hall significantly more slowly than the unprimed group. Now, they knew that other people would find this surprising, so after they got their result, they immediately set out to replicate it. They just straight up ran the study again, and they found the exact same pattern of results. So the study was highly reported on at the time and has since been cited over 5,000 times. This is a really big number and gives some proxy as to the study's impact on the field. And this is a surprising and fascinating result, right? The idea that even thinking of things outside of conscious awareness can influence our behavior has far-reaching and interesting implications. Okay, fast forward almost 20 years to 2012. Bargh's studies were actually run in the early 90s, even though they weren't published until 96. A group led by Professor Stéphane Doyen set out to rerun Bargh's experiment. Doyen's research group is in Brussels, so they ran the study in French instead of in English. They translated some of Bargh's words from the original study, but they couldn't use all of them. So for instance, one of Bargh's prime words was Florida, which isn't likely to have the same connotations in France as it has in the States. So they also ran a pilot study to collect data on the words most closely related to the concept of old age and included those as well. They had 2 different conditions that measured the dependent variable in 2 different ways. One was using infrared sensors to measure walking time. So the participant tripped a sensor when they left the room, and they tripped another one when they got down the hall. In another condition, they had experimenters set up with stopwatches, as Barge did. And the experimenters knew whether participants were in the age-primed group or the control group. Then they gave the following instructions that clearly directed the participants to walk to the end of the corridor. Now, when they ran their replication attempt using the infrared sensors, they found no effective priming. The people in the age-primed group did not walk any more slowly than the people in the unprimed group. When they asked the experimenters to time the participants and explicitly told them which priming condition the participants were in, the effect of age-related priming returned. So they failed to replicate the Barge finding with infrared sensors, and they successfully replicated it when the experimenter taking the measurements knew what condition the participants would be in. Now, it's important to note that Barge maintains that his experimenters were blind to condition. That is, they didn't know which condition the participants were in, as they did in the Doyen study. But the way that Barge's methods section was written makes it somewhat difficult to be sure that the blinding was successful. So then, Doyen published his results with the provocative title,
Yikes.
Yeah, so the strong implication here is that Barge's results weren't due to participants being influenced by primes, but by experimenters being influenced by their expectations. So when this was published, Barge reacted quite negatively. He wrote a blog post with the equally provocative essay title, Nothing in Their Heads,
Yikes.
and went on to deliver a scathing attack on the credentials of the authors and their capability for conducting good science, on the journal that the article was published in, and even on the science bloggers who covered it. In fact, in the psychological community, the fury of his response has been commented on as much as the failure to replicate. So this turns out to be a really interesting case study for talking about replication. In class, we'll talk about the many reasons this finding may have failed to replicate. But remember that if study 1 finds one thing and study 2 doesn't find the same thing, it doesn't automatically mean that study 1 was wrong. So we'll unpack why these studies may have found different results and what we can conclude about age-related priming. We'll also talk about why Barge responded the way that he did, which brings in issues related to the incentive structure of science and the motivation of scientists. Remember to post your thoughts and questions on Slack, and I look forward to talking with you in class.